Hi everyone, and thank you for tuning in to this Macalloy webinar. Today's subject is fatigue in tension rods in brushes. So just to introduce myself, my name is Harry Smith and I'm a design engineer here at Macalloy. I've been at Macalloy for over 6 years now, and generally I spend my days giving technical input on the use of our product to any sort of engineers, architects or customers that need it, designing sort of bespoke solutions for non-standard applications. Quite a few of those do come across my desk, and as well as that I develop the existing products and any new products that we may need to supply. So the agenda for today's webinar is as follows. I'll go through a quick overview of what fatigue actually is and why it happens. I'll then talk a little bit about the design codes and the standards that relate to fatigue in tension rods. Then I'll get a little bit more specific to the product itself, and I'll go through the various factors that have an impact on fatigue performance and also how we typically overcome them. It's important to relate all that theory into actual practice, and to do that I'll go through a real-world example of when it was all put into place for one of our flagship projects, which also happens to be a personal favourite of mine too. And finally, a swift summary at the end just to recap on everything. So first, an overview of fatigue itself. No, I'm not talking about when you're tired because you stayed up too late the night before. Materials fatigue instead is a mechanism of failure that comes about because of cyclic, otherwise known as oscillating loading. EN 1993 Part 1 Part 9 defines this as the process of initiation and propagation of cracks through a structural part due to the action of fluctuating stress. Just to elaborate on that, EN 1993 is the European standard for steel structures, and Part 1 Part 9 is a section in this that covers fatigue. So as this cracking makes its way through the material, you get this kind of seashore effect, leaving behind striations on the fracture face where the crack is initiated from originally and then propagated through the failed part. This crack reduces the cross-sectional area at that point in the component until it gets to a stage where it can no longer cope with this applied load. At this point, it experiences what's known as a catastrophic failure. You can see a couple of examples of this from the images on the right hand side. So that first image on the top is just a diagram that shows how the crack propagates through the material, leaving behind those striations, and then you get the final area where that catastrophic failure occurs. And the bottom image is an example of when it actually happened. So in that image, you can see that the crack actually started right at the top of the image, and it grew through the cross-section of the bar until the remaining material could no longer cope with its applied load. Then it completely snapped, and that final fracture is that sort of bottom darker section that you can see there. Now all of this may sound very dramatic, and more often than not people tend to think dramatic events as quite rare. However, fatigue is actually one of the most common methods of failure in all mechanical structures. Now we know what fatigue is, let's talk a little bit more about why it actually happens. If you take the description of fatigue literally, it's actually extremely common, and by taking it literally I mean a load that oscillates in its intensity rather than being completely static. Now a lot of structures do actually experience a small amount of fatigue as a result of loading such as wind, for example. However, if the load itself, or the change in loads, is relatively small, the loading conditions can be considered what's known as quasi-static. Now quasi-static basically means that from a design perspective you can consider it to be essentially static. Fatigue loading becomes more demanding on the structure as the stress range, the peak load, and the frequency at which it changes its load increases. Now we'll talk a little bit more about where you can typically find that a little later on in the presentation. First, we'll look at the engineering standards and design codes when you need to consider fatigue. Now there are two main standards to consider when it comes to fatigue and tension rods when you're looking at European standards. First of which is the already mentioned EN 1993 Part 1 Part 9, which is the section that covers fatigue in general for structural steelwork. Of the two standards I'm going to talk about, this is the one that's more extensive for fatigue assessment when it comes to tension rods. Now stress range, which is a key term you're going to hear me saying an awful lot today, is the difference in stress experienced by the material as the load increases and decreases in its fatigue cycles. Once all of the structural checks have been performed and you've managed to ascertain the difference in load or the load range that the bar is likely to experience in service, this load can then be transferred into a stress range. This stress range that the bar will be subjected to in its service life is referred to as the detail category. Now the detail category is an extremely important piece of information because this is used in all theoretical works going forward. As well as the stress range, another key piece of information is the number of cycles that the member is actually designed to withstand. For tension rods, this is typically around 2 million cycles. However, it does vary on application. You can compare the stress range on a material against the likely number of cycles to failure using an SN curve. Now, the SN curve that you can see on the screen is the one that's found in EN 1993 Part 1 Part 9. Now, on this graph, it can give you an approximation of how many cycles a component is likely to withstand found on the x-axis, when subjected to a given stress range found on the y-axis. Now, while all theoretical data, including the SN curves, considers the actual stress range, so the detail category that I've already mentioned, the stress range used for testing is actually 25% higher than this. Now, this in essence works as a safety factor, as fatigue is a very common but sometimes unpredictable phenomenon. The second of the two standards that I'm going to be talking about is EN 1993 Part 1, Part 11. Now, this is the part that relates to tension components within a structure in general. And in Part 11, it's Section 9 that outlines the fatigue requirements for tension components. And in that, it gives the detailed category that's meant to be used for tension rods when testing them. Now, while it's always good to adhere to European standards, the stress range specified in Part 11 is actually extremely hard to test. This is because the testing stress range specified is in excess of 131 newtons per millimeter squared. Now, that stress range is very taxing on the system, and as a result, designing and producing a fatigue system that adheres to Part 1, Part 11 is much more difficult than designing a system that specifically meets the fatigue requirements of an individual structure. This is definitely worth bearing in mind when specifying the requirements of a rod system to be used. By no means is this an exhaustive list, but these are a few examples of structures that typically experience fatigue. Footbridges and suspended structures such as staircases, they tend to have a high frequency in change in load, and this is typically as a result of the regular foot traffic that they experience. However, that stress range is often very small as it's caused by the weight of people or perhaps bicycles, so typically it's not too taxing on the material. Now, the reason the stress range experience is so small is the fact that that cyclic load is very small relative to the dead load. So that means that the change in load in the material, and therefore the change in stress in the material, is small. And that means that it can often be considered as quasi-static. Canopies and facades, or other aspects of a structure that are typically exposed to the elements, they often have a larger stress range, as the wind or the snow load that they can be subjected to can often result in large changes in load versus their nominal position. Now, while large, these changes are typically not that frequent. That brings the frequency down, and that puts it under that quasi-static umbrella. However, if the structure hits or is subjected to its resonance frequency, serious issues can arise. I imagine a lot of you have heard of the Tacoma Narrows Bridge, informally known as Galloping Gertie. Now, this is an example of where the frequency of the cyclic loading actually matched up with the natural frequency of the structure itself. So those two forces accumulate into the phenomenon that's known as resonance. Now, this results in much larger stress ranges, higher frequencies, and an expedited fatigue failure. Now, we did actually experience this in a project in the Czech Republic where the design of the surrounding structure, along with some inconsistent preloading by the contractor, resulted in the bars themselves experiencing resonance. So one of the bars had a slightly different level of tension in it than the rest. Now, this altered its natural frequency, and it lined up its natural frequency with the fatigue loading that it was subjected to. This hanger itself oscillated quite violently, and that resulted in a fatigue failure in the bar itself. Note how the bar is creating a waveform similar to that of a sound or maybe even a sine wave. The problem was identified though, and dampers were designed into the surrounding structure, as well as the preloading was corrected to alter its frequency and avoid that resonance occurring again. Finally, road and or rail bridges are structures that have high stress ranges due to the large loads of the vehicle using them, along with a high frequency that comes with high volumes of traffic. This high number of cycles at a large stress range can often lead to fatigue failure. Now, this is where a fatigue system becomes necessary. Please bear in mind that these are just examples. Each structure should be assessed based on its own conditions. Now we'll talk about what factors in the tension rods affect its fatigue performance and also how we go about addressing these. The first of the factors we'll talk about today is the bending moment. This is an additional source of stress caused by a force trying to deflect the material that is cumulative with stress caused by the axial loading of the tension rods. Now, on occasion, it is manageable if the fatigue requirements are low or if there's a lot of redundancy in the member. However, if the fatigue loading is harsh, a bending moment amplifies this significantly. The reason behind this is, as the load oscillates, and then the stress does with it, the two stresses change independent of one another. So if the stress range because of the axial load is 50 newtons per millimeter squared, and then the stress range as a result of the bending moment is 50 newtons per millimeter squared, that localized stress range is 100 newtons per millimeter squared, and that's much more likely to lead to cracking than if the bending moment wasn't present. More often than not in tension rods, such a bending moment is caused by the fittings at the anchorages being misaligned and that angle being taken up by the more flexible bar. So how do we solve it? Well, as the end fittings on a tension rod are more often than not a clevis fork and pin, we find that the best solution to accommodate a misalignment situation is a spherical bearing system. Now, the plain spherical bearings that we use are made up of two rings that rotate about one another, so the inner ring and the outer ring of the bearing stay normal to the pin and gusset plate respectively. These bearings can rotate up to an angle of 5.9 degrees, and then the load is transferred through that angle. And because a perpendicular interface is kept to each part of the bearing, no bending moment is introduced into the bar. So with the spherical bearing system, the area that experienced the bending moment in a standard system no longer has that additional source of stress. Now that reduces the peak stress and stress range, thus improving the fatigue life of the system as a whole. If you'd like to know more about spherical bearing systems, please get in contact after the webinar, where we have a range of literature or myself to elaborate further on how it works. While we're on the theme of physical factors of a system, let's talk about the fact that the geometry at any point in the load path can actually affect the performance in fatigue. Sharp corners in the geometry of a component, such as the one shown in the image there, typically where a section changes in diameter or thickness, acts as a bottleneck for the stress going through the component. While the stress does even out in areas away from the transition, the stress is compounded at the corner, forming what's known as a stress razor or a stress concentration area. Now you can see this from the FEA image on the bottom there, where the edge of the smaller section is far more highly stressed than the rest of the component. Very similar to the effects that bending moments have, a concentration of stress at one point correlates to a larger stress range as the load fluctuates. Now this in turn reduces the fatigue life as stress razors are hotspots for crack initiation. The solution? Well, you've got to change the geometry and design away any of these stress concentration areas. To fix this, you need to ensure that any sharp edges on the load path are removed, and that any changes in diameter or thickness are made more gradual. As an added measure, it's good practice to radius or fillet any corners and the component to avoid any sort of stress concentrations developing where you wouldn't expect them to normally. Removing these stress concentrations reduces the stress range experienced at these given points, and that extends the fatigue life by reducing the likelihood of a crack forming. Now we'll turn our attention more to the material itself, and a factor of this that can affect the fatigue life is the presence of any residual internal stresses within the material. You can see there an example of what residual stresses can actually do. So the outside faces of that section cooled faster than the inner faces, and as a result they generated residual tensile stresses. These stresses were trying to bend the outside faces of the section away from its centre. However, the rest of the geometry was stopping that from happening. Once the material was cut though, as it was in the image shown, the internal geometry is no longer restricting this movement, and the residual stresses actually took over and deformed the material. Depending on which manufacturing route was taken, particularly when considering the sort of cooling rates from the elevated temperatures in the manufacturing process, it's possible for residual stresses to form within the grains of the steel. As the raw material is sat on your shop floor, it's not moving there, so it's lying in static equilibrium. Now, for this to occur, the stresses within the material have to be balanced. Now, for the stresses to be balanced, both compressive residual stresses and tensile residual stresses have to be present. Now, thinking about how fatigue damages a material, it's cracks that grow throughout the steel. So, compressive forces in the steel matrix, forcing the grains together, actually do improve its fatigue resistance. But no yin is without its yang, and the tensile stresses that go with these compressive stresses exacerbate the growth of cracks. And as it only takes one significant crack for a fatigue failure to occur, residual tensile stresses are an absolute no-no. As a result, for a fatigue system, these stresses need to be removed. This is in order to minimize the likelihood of any crack forming and propagating in the steel. The most common method of doing this for tension rods is to normalize the material. Normalizing is very much likened to annealing, where the material is taken up to a predetermined temperature and then it's soaked there for a predetermined length of time. But normalized materials are then air-cooled down to ambient temperatures, instead of cooling the material more slowly in the furnace, which takes place during the annealing process. During the normalizing process, all of the grains in the material are allowed to form to a consistent size and shape as they are held at temperature, and that homogeneity is retained through the gradual cooling process. You can see that from the images as the cold rolled material has grains of all shapes and sizes, versus the two annealed materials that have much more consistent grains. Normalizing is generally performed to increase the toughness of a material, otherwise known as its resistance to cracking. Now, this resistance to cracking improves its fatigue resistance. Another factor of the material itself that needs to be accounted for in fatigue is the potential for any hydrogen embrittlement. When it comes to the material on site, yes, it does need some kind of corrosion protection, and galvanizing is probably the most common use for steel. However, in the galvanizing process, there is a step known as the pickling step, which is essentially an acid cleaning of the substrate before it's galvanized. This can be observed as step 3 on the upper image. The acid used for this process is typically hydrochloric acid. As you can probably tell from the name, the acid is hydrogen based, so using it as a cleaning medium introduces hydrogen into the matrix of the steel. As hydrogen is introduced, it then diffuses towards the grain boundaries and then bonds with the carbon in the steel to form methane. This methane isn't mobile within the material, and as more and more of it is created, it generates enormous amounts of pressure and alters the mechanical properties of the bar, such as its ductility, yield strength, and tensile strength. And as the name embrittlement suggests, it does also make the bar more brittle, and this is detrimental to fatigue resistance as it makes cracking more likely. For hydrogen embrittlement to occur, you need three things to be present. You need a material that is susceptible to it, hydrogen has to be introduced into the steel somehow, and finally, you need a tensile stress on the system. Now, much like the fire triangle, where if you remove one of the three prerequisites, it will not happen, you can prevent hydrogen embrittlement by removing just one of these three factors. The whole point of the system is to be used in tension, so you're not getting around the tensile stress. And changing the material, that can change the entire dynamic of the system as a whole. So as a result, removing the source of hydrogen will always be your best bet. Even if the material used is generally not considered to be susceptible to hydrogen embrittlement, which is actually the case for our tension rods, even the smallest amount of embrittlement can increase the likelihood of cracking and then therefore reduce the fatigue life of the system. As a result, you do need to address it and minimize any chance of it. And the usual solution for this is to remove any process that introduces hydrogen into the bar. Now, while it is possible to galvanize without the pickling process, it tends to be expensive, difficult, and also the outcome is rather inconsistent. So the best way to go about it is to find another corrosion protection method, such as painting or other coatings of the material such as metal spraying. The final factor of tension rods that is considered for a fatigue system pertains to the thread itself, or more importantly, how it's created. So there are two main methods of achieving a thread form from a solid bar. The first of which is a cut thread. Now this is where you start with a bar that is the same diameter as the major diameter or peak of the thread, and you achieve the thread form by removing material with a cutting tool. Now in doing so, the tool is breaking through the grains of the steel and leaving exposed grain boundaries on the flanks of the threads. Now this is an issue in fatigue applications, as these exposed grain boundaries are areas that cracks can initiate. The second option is to roll thread the bar. Now this is where you start with a smaller bar, approximately around the effective diameter of the thread, and the bar is then introduced to three dies known as rolls, and these dies are spinning circumferentially around the bar, and are then forced into the material. So the rolls manipulate the steel. The material that is displaced, creating the minor diameter or the trough of the thread, is then forced upwards to create the major diameter or peak of the thread. So this is the method that we actually use at Macalloy, and as well as the weight and cost savings of using less starting material, the grain boundaries are not left exposed on the flanks of the thread as they are with the cut thread. Now you can see this from the image in the bottom right hand corner there, where the grains of the steel have been deformed and rounded as the thread has been rolled on. Now this means it's more difficult for a crack to initiate. Right, enough theory, let's talk about a job where it was actually put into practice. The project in question is the Troja Bridge in the Czech Republic. So on the left, you can see an artist's impression of the bridge back before ground was even broken. So you can see that from this that it's both a road and rail bridge. So as we talked about earlier, high stress range, high frequency. The bottom right image shows the complex web of the tension rods used during the construction of the bridge. And then finally, the photo that we use in pretty much all presentations that we do, the bridge when it was completed. Now, I know I'm biased, but it really is a stunning structure. It's used in car commercials for a plethora of famous manufacturers, including BMW, Audi, and Mercedes, just because it is such a good-looking bridge. And please note that other car manufacturers are available. We've not been sponsored to advertise here. The first part of the system that was considered was the fork. Now, the fork itself generally experiences low levels of localized stress. That's because of its geometry. It's got an awful lot of cross-sectional area to spread the load across. And as a result of this, the design of the fork fork wasn't in need of a change. Instead, it was imperative to ensure that the material itself throughout the fork was homogeneous and that the casting integrity was to a very high level. In order to accomplish this, the most highly stressed areas on the component were checked with an additional source of NDT. Now, this comprised of magnetic particle inspection, X-ray, and ultrasonic testing. Then, to round off the integrity checks, we also ensured that the surface finish was to a sufficiently smooth profile so that it didn't encourage any sort of crack initiation, and then all the connection points, such as the pinhole and the thread, were concentric with where they should be. The next step was the turnbuckle. So we mentioned stress razors earlier, and the standard turnbuckle is a prime example of this. So in that corner where the chamber meets the thread, you get a stress concentration area like was discussed earlier. As a result of this, the fatigue turnbuckle was designed with a curved transition from the threaded section into the chamber to ensure that the stress didn't concentrate at one point. As well as this, the stresses in all of the turnbuckle under normal loading situations are actually much higher than the aforementioned fork. So in order to reduce that stress in the material, the fatigue turnbuckle had an increased outer diameter to increase the cross-sectional area. Now you can probably notice this on the two diagrams with the difference in wall thickness. The material was also reviewed, so the material that was selected for the fatigue turnbuckle was softer and tougher than what's used for a standard turnbuckle. Now this lower hardness as well as increased toughness means that the chances of crack initiation and propagation reduce. And finally, the thread form itself is addressed. So the standard metric thread form on our tension rods is relatively pointy, let's say. So it has sharp corners at both the roots and the peaks of the threads. Now, these sharp corners would actually act in a fatigue situation as a stress razor. So as a result, the form was altered for our fatigue system so that the root and peak radii of the threads were larger and more rounded. Now that reduces those localized stresses. And the final component within the system to address was actually the bar itself. So firstly, we always work very closely with our material supplier to ensure the cleanliness of the steel. So the cleanliness avoids both micro and macro inclusions within the grain of the steel that would act as stress razors. The bars were normalized, as we discussed earlier, and that was in order to remove those residual stresses that we talked about earlier, which are such killers in a fatigue application. And after the material went through that normalizing cycle, it was then tested to ensure that the process didn't take the mechanical properties below the specification, which it didn't. And finally, for the corrosion protection method, a paint system was adopted. So firstly, to avoid the pickling process so that the chance of hydrogen embrittlement was removed, and secondly, so that the aesthetics of the bars were in keeping with the rest of the structure, and the steelwork looked to be one architectural mass. Once all the design work was done on the system, a representative sample of each of the configurations that were going to be used on the final bridge was manufactured and then tested to prove it met the needs of the application. To do this, it was installed into a test rig as depicted on the right hand side image there, and it was subjected to 2 million cycles at the appropriate stress range, which, as mentioned earlier, was 25% higher than the stress range it was anticipated to experience in its service life. Once those 2 million cycles had been completed, the standard tensile test was performed on the tendon in order to verify it had retained sufficient capacity. Obviously it all passed and the bridge was able to be built, and for additional data, strain gauges were installed to monitor the steel during this test process. Finally, once installed, the bars were preloaded, as hangers typically are on most bridge applications. Now, preloading is the process of actively putting tension into the bar before construction is complete and the structure is put into service. Now, this is typically done in order to minimize or mitigate any amount the bar will stretch during the life of the structure when subjected to load, as this elongation has already been taken out via the preloading process. This is also very relevant in a fatigue application, as in Table 8.1 in EN 1993 Part 1 Part 9, it is stated that for preloaded bolts, the reduction of stress range may be taken into account. Now, preloaded bars are already under stress, and this stress will not change unless the force in the member has been overcome or a secondary source of load, such as a bending moment, is applied. As a result of this, the actual stress range while in service can be minimized through preloading, and now this significantly reduces the fatigue demands on the system. So, to summarize, stress range, maximum or peak load, and frequency are key values when assessing the fatigue performance of a tension rod. The geometry of components on the load path affects the fatigue performance as well as the properties of the material itself. Stresses in the material coming from loading other than axial tension tend to significantly increase the localized stress ranges. and high, localized stress almost always results in a high stress range, which is detrimental to fatigue life. In addition to good theoretical practices, it is essential to test the system to determine it fit for purpose. And finally, if you can preload a tension rod on site, you reduce the stress ranges experienced in service and reduce the fatigue demands on the system. And that's the end of the presentation. So thank you so much for logging in and listening to my monologue. I know I can waffle, but I get carried away when I find something interesting. On screen now, you can see my contact details as well as the general technical inbox that all of my colleagues in the engineering department here at Macalloy have access to.